Hey everybody, Milk's here.
And MoNaCo too.
Ooh, still in Unit 9. It's video number 6.
AJT.
What on earth is equilibrium?
And why is it important?
Yeah, it's got a funny word right in there, doesn't it?
Equilibrium. Equilibrium means to me balance, or equal parts, like two sides of something are the same.
Yeah.
I can balance because my ears are in equilibrium. I can keep my balance.
Right.
So that's what I think of as equilibrium.
Yeah, I see that word equal, and so I think that there's two sides. Whenever I see an equal sign, there's something on one side and something on the other.
Mm-hmm.
What we just got to get through today is understanding that it's the rate.
Right, for chemistry.
Yeah.
What is chemistry equilibrium? So this is a situation where two reactions are happening at the same time, opposite directions, and it's always shown by this symbol. What's that, Mr. Miller?
What, the double-headed arrow?
Yep.
Yeah, a lot of times you'll see the arrow only has one tail on it. There you go. That's what you're really going to see a lot.
Yep. I sometimes draw it like this too.
Yep, word, it makes it easier to draw it a little bit like that.
Or even sometimes
Right.
like that.
Right, but let's not let technology.
These are all ways of showing a two-way street.
That's it. Both directions, same
Two
time.
reactions happening at the same time in opposite directions.
There you go. So, as reactants collide to form products, some different product is going to go through the reverse process to form reactants.
Right, so collision theory says you got to collide with the correct orientation and energy for a reaction to occur. But this part of the whole equilibrium unit is saying that, listen, things can fall back apart. A synthesis reaction puts two things together.
And can decompose.
And then that thing that you just made can then decompose. All we're saying is that it's potentially happening at the same time. For every two atoms that come together to make one molecule falls apart to make the two atoms that it was made from. So this cyclic back and forth,
right.
teeter-totter, seesaw.
Right. I think it's important to notice that it's a different molecule that's breaking apart in that reaction. It's not the same one. It doesn't just come together and then break apart instantly. When it comes together, it almost forces
somebody else to fall apart. Right. And then maybe a few million seconds later or something, it's turn to happen.
Right.
It
happens again, it happens again.
Constantly.
But now the important part for us is, because these two events are happening at the very same time, the concentrations of the reactants in the product remain constant. They do not have to be equal, but they just don't appear to change, because as one happens, the other happens in the reverse direction, so it doesn't look like anything's actually happening.
Let me draw just a quick picture to show you. For every A that combines with a B, it makes an AB. For every AB that already exists, it falls apart in the reverse reaction to make an A and a B.
Correct.
So the numbers of A's plus B's themselves is not really changing over time.
No.
Because for every two that come together to make an AB on the other side falls apart to replace.
Right, and they don't have to be equal amounts of A plus B equals the same amount as A plus B. That is not the case. They could have a very low concentration left of just A plus B. But every time they come together and form an AB, a different AB is going to split to break apart to form an A plus a B.
Yep.
And so their concentrations can be different, but they have to be constant in order for it to be equilibrium.
It doesn't look like they're changing.
Right.
Which is tough when we're talking about equilibrium.
True.
So a phase equilibrium is a physical equilibrium. It's like when you have a solid becoming a liquid, and at the same time that liquid's becoming solid. So like this is like water at exactly 0 degrees Celsius.
Sure. When we did those phase diagrams, or not so much the heating curve.
Yep, the flat parts of the curve was where there was a phase equilibrium occurring. And that's why we drew the double-headed arrows in that part of those curves. Because for every molecule of water that froze, there was a molecule of water that was melting in turn.
Right, until there was enough
energy to push the equilibrium in one direction
There you go.
up the hill or down the hill, so to
Just
speak.
basically enough energy to break the equilibrium.
Exactly, and
get
we will
through
see that what it takes to do that later on.
Right.
But this is just about equilibrium. So what's a solution equilibrium?
That is when the rate of the dissolving equals the rate of a crystallization. So this happens generally when we have a saturated solution that has some more solute at the bottom. So if you put sugar in your cup and you make it so you saturate the water with sugar and it won't dissolve anymore, and then you put a little bit more sugar in, you're going to end up creating an equilibrium. The solid sugar at the bottom, for every one molecule that dissolves and goes into solution, a different molecule in solution has got to recrystallize out, and then it'll look like nothing's happening, but something is technically happening. You're forming an equilibrium
You've got basically a pile of sugar on the bottom.
because you put so much in.
Because at the microscopic level, like Mr. Milk said, every molecule that dissolves, a molecule actually recrystallizes. And this only happens when the solution is saturated.
Right, it has to be saturated.
For this
Otherwise
physical equilibrium.
because otherwise it'll just dissolve and won't force it out of solution.
So when we
but
were
different
working
on the
with
other side.
that solubility curves, those are basically showing you solution equilibriums. Potentially. If it was saturated, it was at a solution equilibrium.
Correct. Okay. So now to the nuts and bolts of this unit. Chemical equilibrium. The rate of the forward reaction is going to equal specifically the rate of the reverse reaction.
Right. And this is difficult to show graphically.
So that's what these graphs.
That's what these graphs show. Basically, you're looking at the slope of the curve there in that first yellowish part.
And that's where the reaction is actually occurring.
They're equal in opposites
until they get
to equilibrium, in which case the concentration is constant.
Doesn't change.
That's
You
why
notice
it flattens out to
we have one
zero.
example where the concentrations end up being the same.
Right.
And then the first example, A, once it reaches equilibrium, the concentrations of reactants and products are not the same.
Right. So that first part of this graph is where the reaction is establishing an equilibrium.
Correct.
The reactants are coming together to make the product or
We're
products.
seeing a change in concentration as they're being
seeing it
consumed
change.
and made.
And then as soon as that equilibrium is established, you got that dashed dotted line. And then the green part of that graph shows that, listen, the concentrations of A and B aren't changing anymore.
Right.
They had their chance to change, establish the equilibrium, and now that they've done it, we're good.
Right. So these graphs, you might see them.
Might, potentially.
And they're kind of weird looking. We don't see things generally where we have two graphs at once.
So when you see concentration versus time versus on a double line graph like this,
if they become equal,
at some point, or the slope becomes zero at some point, you know that you're looking at an equilibrium.
Yeah, I misspoke. Yeah.
Because the concentrations where those A's and B's actually line up won't necessarily be equal, but the slope of the line, meaning the change in the concentration,
the change in concentration
is not
stops.
changing. So therefore, we know we've got an equilibrium.
And time is still marching on. The reaction is still going. Okay. So what we need to know about this whole equilibrium thing. Reactions that are equilibrium must be reversible, i.e., no gas, heat, or light given off.
You can't lose anything.
Yeah.
These
Or
equilibrium
I can't go backwards then. I get a product that makes
goes
it so
away.
then I can't do anything. I can't go
So
backwards.
most of these types of reactions happen inside sealed containers.
Yeah, solution chemistry a lot of times.
Yeah, I mean, phase equilibrium has to happen inside a sealed container.
Especially for the gas part.
Because if it's making a gas, it's got to have something condensed on it, form back into a liquid. A chemical equilibrium can happen inside of a jar, inside of a solution itself. So you might not have to have a lid on the top of that one, but it would help.
Yeah, it would.
Sure.
But the liquid itself would act as the container for the ions.
Right, until things evaporated. But we're getting too far out into the weeds there.
And next,
the reaction continues. We've said this a few times. Once equilibrium is achieved, the reaction continues. To the naked eye, it doesn't look like anything's happening, and I think that's what's hard to understand about equilibriums, because all the chemical reactions you've seen so far go in one direction. You saw that something happened. It was obvious.
You saw light or a color change.
Bubbles or
something
gas.
Precipitated.
Obvious. And then it was done.
Right. That's another one, actually. An insoluble precipitate would be an irreversible reaction.
Right.
That's a good one. We missed that one out.
So the reaction only appears to stop because the concentration of products and reactions stays constant. So whenever you're doing or creating an equilibrium, that first few seconds that you see something change is when the equilibrium is becoming established. After it looks like it's quote-unquote done, it's actually continuing with the equilibrium.
So basically, we just discussed a theory about what an equilibrium is.
Yep.
Next notes, we're going to find out what happens. Once I've established it, what happens when I play with it.
Yeah, can I mess with them?
There you go. See you guys.